This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 7, Lecture 1. Lecture 1 of Chapter 7. In this chapter, we will cover ionic bonding, covalent bonding, Lewis symbols and structures, formal charges and resonance, strength of ionic and covalent bonds, and molecular structure and polarity. These topics will be covered, but not necessarily in this order. So let's start with the discussion about Lewis structures and covalent bonds. A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. In other words, two atoms, two elements from the periodic table, come together and they share their electrons such that they form a bond. That is what a covalent bond is. Elements in group 14 through 17 form molecular compounds, molecular bonds, covalent bonds. Atoms share valence electrons in order to form covalent bonds. In other words, not all the electrons in the atom necessarily participate in bonding, but those that are known as the valence electrons participate. Valence electrons are the outer shell electrons of an atom. The valence electrons are electrons that participate in chemical bonding. So when a chemical bond is formed, that means the valence electrons have done their job. They have participated. And you've already learned in previous chapters how to identify valence electrons. So that brings us to a Lewis structure. A Lewis structure is a systematic drawing of a compound that shows the connectivity of the atoms and the chemical bonds in a covalent compound. That's a fancy way of saying Lewis structures let you draw chemical structures that don't violate any chemical rules. One of the critical rules of drawing Lewis structures is not to violate the rule of 8 in most compounds. However, there are several exceptions to that rule. So the bottom line is Lewis structures let you draw out chemical structures so that you can see where the electrons were used, the valence electrons that is, were used in making the compound. And when they come together, they form bonds. Again, the valence electrons are the outer shell electrons of an atom. They're the ones that allow atoms to form bonds. We show you here the electron configuration of the main groups that we will talk about in freshman chemistry and that are particularly useful for this lecture. Group 1, 2, 13, 14, 15, 16, and 17. Group 18 is omitted because it has 8 electrons, which fulfills the rule of 8 for the octet rule for noble gases. Noble gases do not participate in bonding. We also omit the transition elements from this discussion, which include group 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We also like to remind you that to determine the number of valence electrons, count the electrons in the highest end period. And that gives you the valence electrons based upon its electron configuration. So we show you here simply what those results are, and you can either memorize them or you can write the electronic configuration out, but the numbers don't change. Group 1 and group 2 are always 1 and 2 valence electron, 13 is 3, 14 is always 4, 15 is always 5, 16 is always 6, and 17 is always 7. Okay? This periodic table shows you the electron dot configuration, and you will hear the term Lewis dots or Lewis dot structure used occasionally, and occasionally I use it interchangeably without even realizing I do it. So if you hear the term Lewis structures or Lewis dot, that is the same thing. Also, if you hear the term dots, that refers to the electrons. I use dots and electrons interchangeably without even realizing it. Okay? So we show you how the dot configuration is laid out according to the periodic table. Just note that group 16, I show you my preferred view of how to draw group 16, but at the end of the day, there is no really magic about drawing these. If you have the right number of electrons, the right number of dots, and they are paired properly, then it works. The reason I prefer the group 16 denoted as I have it is because of how I suggest you learn to write these, and that is coming up in a few slides. Okay? But otherwise, this is what the dot configuration look like. Notice that it's the exact same dot configuration for every atom, every element in that group. The groups are all the same. They all have the same dot configuration, and in their outer orbital, they have the same number of valence electrons. So if you know how to draw it for one, you can draw it for others. Again, you can either memorize it based on where it is in the periodic table, or you can look at the periodic table. Okay? Periodic table will tell you what the answer is. We will be showing you how to draw these Lewis structures, but I want to introduce some more concepts so that once we start to draw, we can talk about these concepts as we draw. Okay? So, multiple bonds and lone pairs are an important part of Lewis structures. In Lewis structures, we form single bonds. Single bonds are formed by sharing one pair, that's a total of 2 electrons, by 2 atoms. So every 2 electrons is a bond, is a share. So atoms need at least 2 electrons to share. After that, they might double up. They might add more electrons, but they always add electrons in pair when we talk about drawing Lewis structures. You will learn in some other level classes about radicals. Okay? Well, double bonds are formed then when we have 2 pairs, 4 total electrons shared between them. It's a double bond only if they're sharing all 4. Triple bond means they're sharing 6 electrons. Okay? So when they share 6 electrons, it's called a triple bond. Not that difficult to figure out why, right? So for every line, we form a single bond. We form 2, we have a double bond. We form 3, we have a triple bond. All right? And double and triple bonds are referred to as multiple bonds. Okay? Lone pairs represent a set of non-bonding electrons, and it must be 2 electrons to be a lone pair. Group 15 through 17 have lone pairs. So when you get to group 15 through 17 and you're drawing Lewis structures, you want to be aware that they may have, and most often will have, and almost always in freshman chemistry, they will have lone pairs. Okay? So be aware of that. Now, lone pairs, again, should be 2 dots. Not 1 dot, but 2 dots. And it's worth mentioning now that when you draw Lewis structures, be sure that you don't leave a single dot unpaired. An obvious giveaway that your structure is absolutely wrong is for the professor to see a single dot sitting by itself. If you have a single dot sitting by itself on one atom and a single dot on another atom, find a way to put them together at least. Okay? But if they're sitting there alone as a single dot, it is absolutely going to be a wrong Lewis structure. Okay? Now, you will get frustrated because you'll say, well, I can't pair them. You must find a way to pair them at all costs, because if it's not paired at the end, if they are not paired at the end, it will absolutely be wrong. So, lone pairs stand alone. They sit by themselves. They do not participate in bonding. Okay? Once these bonds are formed, they obviously have some bond length. And that bond length is related to the atoms that are used in forming the bond. This isn't a hard concept to understand. It simply means you have these two marbles that meet and they have this bond distance from center to center. That's it. So your bond length is the sum of each atom's covalent radii, which is the length from center of the atom to the other center. Okay, so you basically find the centers of the two atoms, measure the distance, and you have the answer. Okay? And we show you the bond length here in picometers for some typical compounds. All right? Note that single bonds tend to be longer than double bonds. Okay? So be aware of that. So for example, if you see the CC bond is 154 and you see the CC double bond is 133 and then the triple bond is 120. That is a trend that we would expect you to know. That single bonds are longer than double bonds are longer than triple bonds. So the bond length, bond distance gets shorter as we add multiple bonds to it. Okay? All right? So be aware of those trends. So let's now start to talk about how we put this together and start to draw Lewis structures. I am going to first talk about this without giving you the rules. For some students, it will be intuitively obvious how to redistribute these dots. It's like playing Legos until they match, making bonds and leaving the proper number of lone pair. And keep in mind, lone pair requires 2 dots, 2 electrons. If you leave 1 dot alone, your structure is going to be automatically wrong. Okay? So I'm going to show you the concepts and start to show you how the concepts come together before I give you a lot of rules. Okay? All right. So what's a covalent bond? A covalent bond is formed when 2 or more atoms share their valence electrons to form a stable compound. Now, we show you what happens if we make diatomic fluorine. Diatomic fluorine is the natural state of fluorine. It exists as a diatomic. Okay? If we take a look at the Lewis structures on the periodic table or we learn to draw them, we recognize that there are 7 dots, 7 electrons surrounding the fluorine atom. If we systematically draw these, which I will show you how to do, it would automatically pair up 3 sets of electrons, leaving you with 1 electron alone. And what do you know already? We don't like to leave 1 electron alone, which gives us a real strong driving force for combining one fluorine with another so that those 2 electrons that were alone can combine to form a chemical bond. You get it? So that's what we show you here in this picture. We take the lone atoms of fluorine, we push them together, and in the middle we form a covalent bond. We note that if we count the dots associated with each atom, we find there are 8 dots around the first fluorine and 8 dots around the second fluorine, which fulfills the octet rule. We will show you step by step how to do this. However, if it's intuitively obvious to you how to do this, don't sweat the rules. Just do it. Drawing Lewis structures is as much art as it is science. Some can intuitively see how to put these dots together where they make perfect sense right away. Do not overcomplicate it beyond that. It is pushing dots around in a way that makes sense for a stable compound. What makes sense for a stable compound is to have at least a single bond between the atoms and have lone pair electrons or leftover electrons around the atom to fulfill an octet rule or fit the exceptions to the octet rule, which you will learn. So there we have fluorine. We put it together. On the outside, we have our lone pairs. These are lone pairs because they're all doubled off. One quick way to check it is to count the numbers. If you can't divide by 2, you missed it. Something got lost. Okay? The other thing we want to do is count the total number of electrons to make sure we don't lose any. We don't throw it away. You cannot discard the electrons. One fluorine has 7 electrons. The other fluorine has 7 electrons. When they come together in the middle, the total electron count must be 14. And if I drew a perimeter around one atom, I must see 8 electrons. The rule of 8 will hold firm more times than not for group 14, 15, 16, and 17. So each time you have an atom in group 14, 15, 16, and 17, check it very closely to see whether or not it fulfills the rule of 8. It is uncommon and rare in freshman chemistry that is not the case. There may be some exceptions, and you will know what they are as we work through it. But in general, that is the first thing you want to do before you say it's all done. You want to check and see whether or not it fulfills the rule of 8. In this case, it does. So the 2 electrons in the middle come together, and when they come together, they form a single bond. Now, note that the direction of the 2 dots in the middle, they are running vertical. I am perfectly okay with horizontals. And more times than not, when I personally write them, I tend to write horizontal by habit. So be aware of that. That whether the electrons in the middle that form the bond are pointing vertically or horizontal, it does not matter. It is okay to point them in any direction you wish. However, I tend to point them horizontal on purpose. It works for me. All right? Note that 2 dots equals 1 shared bond. You want to be aware of that rule. That's how it works. So that's fluorine. And we've drawn the Lewis structure of fluorine without bothering you with all the rules. Again, if it's intuitively obvious how to do this, just do it. Now, one of the things you want to take care in doing is not splitting up your lone pair. If it starts as a lone pair, more times than not, it will end as a pair somewhere in the structure. Okay? So be aware of that. So that does it for fluorine. We've drawn a Lewis structure for diatomic fluorine without using a set of rules to show you how to do it. So if you can do it intuitively, it's perfectly okay. Let's take a look at another example, and we're going to do it simply by intuition, by inspection, by discovery, before we show you some rules that might help. In this case, we start with water, H2O, 2 atoms of hydrogen, each with 1 dot, 1 atom of oxygen, monoatomic oxygen, with 6 electrons, 6 dots. Because oxygen's in group 16, it has 6 valence electrons. All atoms, all elements in group 16 have 6 valence electrons. So we take the 2 atoms of hydrogen and we observe that they will fit conveniently with the 2 available dots, electrons on oxygen, because only 2 of those electrons are alone or free. The others are in lone pairs. So we don't disturb the lone pairs, but we take 1 hydrogen and connect it with one side of the oxygen, one with the other. Okay? And when we inspect this for completeness toward the octet rule, we discover that oxygen has 8 electrons around it, and that fits the rule of 8 octet for things, elements, that is, in group 14, 15, 16, and 17. And we know that hydrogen has 2 around it, which fits for hydrogen. Note that hydrogen is satisfied with having only 2 electrons directly associated with it. So we draw the dot structure, and then we draw the line in, which represents the 2 electrons, and we have water. It's important to note, however, in the drawing we have here, this does not show its proper geometric shape. So be aware of that. This isn't drawn to geometric shape. The proper geometric shape for water is a bent structure. Okay? We take a look at double bonds. In this case, we have carbon dioxide, and to put together carbon dioxide, starting with its oxygen and carbon atoms, 4 dots around carbon, 6 dots around oxygen. We push them together until we pair up all the electrons and move pairs of electrons around so that we can fit the rule of 8. And in this case, we can have an 8, 8, and 8 structure. This gives us a double bond. Again, we will show you how to follow a set of rules to do this. But in the end, doing Lewis structures requires that you simply look at them, shift electrons around in pairs once they're paired. Push singles around if they're single and pair them up until you get a reasonable structure. And a reasonable structure will fit the octet rule for 14, 15, 16, and 17. And it will have 2 for everything in group 1. It will have 4 for everything in group 2. And it will have 6 for everything in group 13. You will learn this as we go. So there we have it. Double bonds then in carbon dioxide, because we have 2, 4, 6, 8 electrons on the center atom with 4 on either side, which means we have a double bond. Then we have a triple bond, nitrogen. Nitrogen, we show you the finished Lewis structure, and we find that each of these atoms, the nitrogens, have 8 around them. They started with 3 available dots. If you draw out the Lewis structure of nitrogen, you discover that it has 3 available dots for bonding. So by intuition, we simply connect those 3 dots to each other, leave the lone pairs on the outside, and we get a triple bond. Again, I'm showing you here how to simply intuitively do it based upon the free electrons and not disturbing the lone pairs. But when we move the lone pairs, we move them as a lone pair, not as an individual dot. So now that you've practiced this and you have an idea what you're looking for and an idea of how to approach it intuitively or by inspection or discovery, let's now talk about some rules that can help guide this. Keep in mind, you're not required to follow these exact rules. You simply have to have a process that allows you to get to a preferred Lewis dot structure. Okay? And these rules can help guide you, particularly if you're struggling and you can't quite just see it. Okay? So rule number 1, draw the dots, valence electrons around each atom. So individually draw the valence electrons. If it's carbon, draw all 4 around carbon. If it's nitrogen, draw the 5 around nitrogen. It tends to work best if you assume that an atom has 4 sides. You think of it, each atom as having 4 sides. Then add 1 dot, 1 electron, moving in either clockwise or counterclockwise fashion so that they will naturally pair. So after the 4th dot, the next ones will naturally pair, and you'll be able to see what your lone pair count is. Okay? So that's just a way of doing it. Okay? But it tends to work best if you use 4 sides when you consider drawing your Lewis structure. So when you see the atom, think 4 sides in general. Okay? Next, or at some point in the process, draw out a skeletal structure. Just propose what you think it might look like. Use your intuition based on what you've seen thus far about chemical compounds. You are starting now to get an intuition about what compounds look like. Okay? So use that intuition. Use the knowledge that you're gaining. Again, we're not teaching the rules to limit you to the rules, but the rules to help guide you. Count the number of single dot electrons to help suggest possible alignments. So you start to move things around to see what makes some sense or starts to make some sense. The 4th thing you want to think about is choose the central atom, which is often the most single dotted structure. In other words, the one that has the most single dots tends to be the central atom. For example, carbon has 4 single dots in its Lewis structure. Oxygen has 2. So I would tend to choose carbon as my central atom, although it might turn out that oxygen is really the true central atom. So be aware of that. All right? By default, if you get stuck, choose group 14 over 15 over 16 over 13 as a central atom if you just get stuck or if you need to make some adjustment as you go. Don't be afraid to shift it around until it makes sense, okay? Put the single dots together first. That tends to work more times than not. And then pair the lone pair of dots as necessary. Dots, again, means electrons. But never leave an unpaired dot. Never leave an electron sitting alone. If it is alone, look for the partner somewhere on another atom or somewhere in your structure and put it there. And do not erase dots or leave dots out simply because you don't know where they go. If you start with a total of 10 dots in the beginning, you have to have 10 dots in the end. Okay? Then, as often as possible, particularly for 14, 15, 16, and 17, make sure you push toward the octet rule of 8. Okay? When you're looking at what's directly around a single atom. Note that group 1 will have 2 electrons and is perfectly happy. That includes hydrogen. Group 2 will have 4 electrons and it's perfectly happy. And group 13 will have 6 electrons and it's perfectly happy. So when we talk about the octet rule, the rule works for 8 or what satisfies its natural electron balance. And the natural electron balance for group 1 is 2 electrons for 2, 4 electrons for 13. The natural electron balance for it is 6. Okay? 14 through 18 like to have 8 electrons. And remember, 18 is the noble gas group. And noble gases do not participate in bonding. So let's practice drawing some Lewis structures using the rules or as you go intuition. But I'm going to guide it somewhat by thinking about the rules, particularly a couple of the key rules that help guide us. And I'm doing this in case you're one of those who can't intuitively see it. Okay? So, we're going to write the Lewis structure of nitrogen trifluoride. It has a nitrogen group and it has fluoride. As a matter of fact, it has 3 fluorine groups. So when we look at the dot structure of nitrogen and we look at the structure of fluorine, we note that nitrogen has 3 dots that are singled out as singles, 3 singles, and fluorine has only 1 single. The others are lone pairs. So it becomes somewhat intuitively obvious that nitrogen should perhaps be considered as a central atom because you can stick more things around it. You can put more groups onto nitrogen, attach more groups to nitrogen than you can fluorine. And since it's a ratio of 1 to 3, and we have 3 available, and we have 1 dot on fluorine, we start to just put it together. So we put the nitrogen group in the middle, okay? And that becomes somewhat the obvious way to go for many. For others, it's not. But if there's 3 dots versus 1 dot, put it in the central atom, okay? We show you the electron configuration here, so you will know what those valence electrons look like. And we know that group 15 has 5, group 17 has 7 valence electrons. And therefore, in our final, we must have 26 electrons in our final count. So we have to be aware of that as we're working through this, okay? You cannot violate your count. So we put it together as we show you here. Note that I tend to draw the connecting bonds as horizontal. You're perfectly welcome to draw them as vertical. So we show you the complete dot structure. Now that we put all the dots around it, we show you where we've now drawn in the lines to represent the bonds in this, recognizing that 2 dots is one shared bond. Okay? And then, just to help us visualize it, we draw circles around each of the atoms to see whether or not we have 8 electrons around each of them. And in this case, we do. That fulfills the octet rule of 8. Therefore, we're satisfied that this represents a pretty good Lewis structure. Interestingly enough, we have 20 lone pair electrons, which means that we have 10 lone pairs on this compound. 2 of the lone pair are located on nitrogen, and the other ones are located on fluorine. Group 17, in general, will have 3 lone pairs associated with it. We're going to show you some exceptions, but for many of the problems you'll do in freshman chemistry, group 17 will typically only bond once, and it will have 3 lone pairs associated with it. So we're satisfied with this drawing for our Lewis structure. Let's take another example. Nitric acid, shown here, HNO3. We have the dot structures based upon where they're located on the periodic table. Hydrogen has 1 dot. Nitrogen in group 15 has 5 dots, 5 electrons, of which 2 form a lone pair. Oxygen has 6 dots, 6 valence electrons, of which we have 2 sets of lone pairs. Okay? By inspection, we believe that nitrogen will be the central atom, or at least be one of the central points of contact, because it has 3 vacant spaces available, because it has 3 single dots, 3 single electrons. We look at oxygen, it has 2 single electrons, therefore 2 opportunities to bond, and hydrogen has 1. So we draw out a connection that might give us an opportunity to do this. You can always move this around. It is not fixed. So you write it out, you take a look at it, and then you decide whether it makes sense. We do a total electron count, and we discover that we have 24 valence electrons that we must account for in nitric acid. So we then draw in the structures showing the Lewis connection with the dots. Then we convert those dots to lines. Each line represents 2 dots. Keep in mind the lines are the bonding connections. Then we note where the lone pairs are in the structure. And then we start to inspect it to see whether or not we have the rule of 8. So once we get this preliminary structure drawn, our next step tends to be to look for fulfillment of the octet rule. So we look at our skeleton drawing, and we observe that nitrogen in particular does not have sufficient electrons around it in the skeleton structure. So since nitrogen currently does not fulfill the octet rule, we borrow 2 electrons from the oxygen, and we move between the oxygen and the nitrogen. That way the oxygen still has its associated electrons, and nitrogen can pick up a set of electrons. That leaves us with the structure that we have drawn. We count the electrons around each atom, and it fulfills the rule of 8, except around hydrogen we have 2, which is perfectly okay with the hydrogen. Now, again, I'd like to point out, You don't have to follow these rules to do Lewis structures. But we thought we'd offer you a set of rules to help you go through the process to see how it's done. There are other ways to go about getting this done. Okay? So keep that in mind. Kind of a general tip when you're trying to figure out which way to add electrons as pairs, look for the area that's either satisfied or over and move it to the area that's under. So you look for an over and under area, and so you take electrons from the over area and you move it to the under area atom, okay? And it's okay to move the electrons around until you get it to work out, all right? As long as you don't leave them in one single dots, and as long as you recognize that moving in lone pairs is better than moving single dots. Not all compounds and elements will fulfill the rule of 8 octet. The rule of 8 octet is based upon the noble gases. There are other energetically stable and favorable structures for compounds on the periodic table. Group 2, as we pointed out to you, is perfectly okay and balanced to have 4 electrons associated with its central atom. We show you in this case where we have BeH2, our beryllium hydride here. We note the beryllium has 2 electrons. We have 2 hydrogens, which accounts for 2 times 1 electron. We have a total balance of 4 electrons. It's perfectly happy because it fulfills that balance of electrons associated with the central atom and the electron count. Group 13. We show you here BF3. We count the valence electrons associated with boron and with fluorine, and we discover that we must have a total of 24 electrons for this compound. We have the 24 electron. We note that fluorine is perfectly happy with its 8 electrons around it. The central atom here, however, is very happy to have a total of 6 electrons, 3 directly attached and a total of 6 shared. Group 13 on the periodic table is perfectly stable and happy to have 6 total electrons associated with it. So you want to make sure you're aware of that. You may recall that I said be sure to pair all the electrons, but there's even an exception to that rule. Nitric oxide or nitrogen monoxide is an exception to that rule, and we show you that exception here. It works because we have the 5 valence electrons still associated with the nitrogen, and we have the 6 valence electrons still associated with the oxygen. Again, that's an exception. But on the other conditions, be aware that you want to work hard to pair those electrons off. Okay? Then there's this expanded octet opportunity, particularly for atoms in group 16, as we show you here for sulfur. Also note that there's an opportunity for atoms in group 15. We show you that for phosphorus. So we work through the numbers on sulfur with 6 fluorines associated with it. Sulfur hexafluoride. We count through the electrons, and the electron balance works out for this central atom. Likewise for phosphorus pentafluoride, it works out for the balance. Note that in the case of sulfur, sulfur is located in group 16 and therefore would like to have 6 valence electrons, or has 6 valence electrons, and in its expanded octet format, it still has the 6 electrons associated with it as a central atom. Likewise for phosphorus, phosphorus is in group 15, therefore it has 5 valence electrons associated with it, and in its expanded format, it still has those 5 electrons associated with it. Again, these are some of the exceptions that you will see to the rules. Now, when we talk about covalent bonds, it should be noted that covalent bonds have potential energy. That potential energy is proportional to the bond energy or the bond strength for that covalent bond. So, let's talk about bond strength and how to estimate the values. The strength of a covalent bond can be measured by the energy needed to break it. In other words, if you break a covalent bond, measure that energy, that gives you an indication, or that is a measure of its bond strength. The stronger a bond, the greater the energy required to break it. So the amount of energy is directly proportional to its strength. We can use bond energies then to estimate enthalpies of reactions. And that is what we want to show you an example of in the next few slides. How do we estimate that energy? How do we determine the energy or the enthalpies of reactions? The sum of all bond energies equals the standard enthalpy change for the endothermic reaction for bond breaking. In other words, the delta H for that energy can be calculated or estimated based upon the sum of the bond energies. And we'll show you here in some equations where we have the equation XY, a generic equation that decomposes to X and Y, and delta H0 is equal to that bond energy between X and Y. Okay? In other words, the amount of energy needed to break the bond between X and Y equals your delta H. So, for example, if you have hydrogen gas that dissociates to 2 molecules, 2 atoms of H gas, monoatomic hydrogen, the DHH equals your delta H, which equals 436 kilojoules. And those values are reported in tables, standard tables. So if we took, for example, methane, which has 4 CH bonds, and we decompose it to carbon and 4 monoatomic hydrogen atoms, we will find that the delta H0 equals 1,660 kilojoules, which is 4 CH bonds times the bond energy of 415. Again, and that gives you 1,660 kilojoules. So essentially, your decomposition energy equals to the amount of energy found within the chemical bonds. So with that, what can we say then? We can say then that delta H equals the sum of the bonds broken minus the sum of the bonds formed. Okay? So basically, again, delta H equals the sum of the bonds being broken minus the sum of the bonds being formed. And we show you an example here with hydrogen gas and chlorine gas given 2 moles of hydrogen chloride gas. That reaction involves the bond breaking of a hydrogen bond and a chlorine bond, and that leads to the formation of an HCl bond, but there are 2 atoms formed there. The equation must be balanced. So if we take the values from a standard table, we put them into the equation. We have the hydrogen at 436 kilojoules plus the chlorine at 243 kilojoules, noting that it requires more energy to break a hydrogen bond than it does a chlorine bond. That's minus 2 times the 432 kilojoules, which is the energy in a hydrogen chlorine bond. And we do the math and we find minus 185 kilojoules. So that is the estimate of the bond strength for the reaction of diatomic hydrogen gas and diatomic chlorine to form 2 molecules of HCl gas. So let's work a problem. Methanol, which is CH3OH, may be an excellent alternative fuel. The high temperature reaction of steam and carbon produces a mixture of the gases carbon monoxide, CO, and hydrogen gas, diatomic H2, from which methanol can be produced. Using the bond energies on standard tables, calculate the approximate enthalpy change for the reaction. For the reaction of carbon monoxide plus 2 moles of H2 giving methanol. And we have 2 moles of H2 because it requires 2 as a coefficient to balance the chemical equation. So, let's take a look at how we approach this problem. First, we draw out the Lewis structure for the reactions and the products. Now that is very helpful. For some, it will be intuitive without drawing it out. But drawing the Lewis structure is a helpful process. Okay? So, what do we have? We have carbon monoxide, we have its Lewis structure, plus 2 moles of diatomic hydrogen, so H2, gives us the structure shown on the right for methanol. So we know the equation for delta H equals the summary of the bonds broken minus the summation of the bonds formed. We have bonds broken, carbon monoxide. We have bonds broken in hydrogen gas. We look on the tables and we put those values in. We have bonds formed. 3 carbon hydrogen bonds are formed. 1 carbon oxygen bond is formed. And 1 oxygen hydrogen bond is formed. We look on the appropriate tables and we put those values in, and we obtain a delta H for the process of carbon monoxide plus 2 moles of hydrogen gas to give methanol negative 107 kilojoules. Note, a negative value indicates an exothermic process. So this is a favorable process. So this is how we estimate bond strengths. We take the delta H and we know that it's equal to the sum of the bonds being broken minus the bonds being formed, and we get those values from standard tables. We show you another standard table here on this slide so that you are aware of it. So that's how we draw Lewis structures. One of the results of our understanding of Lewis structures and the location of electrons within compounds, atoms, and molecules is it creates a unique physical property known as polarity. When we talk about polarity, we must talk about polar bonds as well. So let's start to talk about this concept of polarity and polar bonds. Okay? When we talk about polar covalent bonds or polar bonds, it is a covalent bond with greater electron density around one of the 2 atoms. And in fact, that's what polarity is. Polarity is having a higher electron density at one atom versus another atom. And therefore, we can talk about it with regard to having polar bonds and polar covalent bonds. Again, polarity is the physical property associated with having a uneven distribution of electrons within a covalent compound. All right? Now we show you an example here, and you will learn the symbols as we go, and we'll give you more definitions to clarify as we go. But we start with HF, hydrogen fluoride, and if we look at its Lewis structure, which we've drawn here, we notice that we have a lot more electrons associated with fluorine than we do with hydrogen. Therefore, hydrogen is considered to be electron poor, and fluorine, simply by inspection, is electron rich. Electrons are negative. Therefore, the negative charge or the partial negative charge in this molecule lies to the right side on the side of fluorine. And if you look at it by inspection, you can see that. So we denote that with a sigma minus, saying that it has a higher or a partial negative charge associated with it. And the sigma plus, meaning that it has a lower or partial positive charge associated with it. A lower concentration of electrons are located at hydrogen than they are at fluorine. Or perhaps we should really say that a higher proportion of electrons are located at fluorine over hydrogen. A couple of tips for you with regard to covalent bonds. Group 14 through 17 form covalent bonds with each other. If it's located in group 14, 15, 16, and 17, it will form a covalent bond. That's the first thing you have to recognize. Is it a covalent bond? Yes. Tip number 2 for you. Any two different atoms always form polar bonds. They may not be highly polarized, but they're always polar by default simply because they're different. So difference in atoms makes the bond between those atoms polar. Okay? Now, the bond may be polar, but that doesn't mean the molecule is polar. And we will show you how to differentiate that later on in this lecture. So let's recap. Polar covalent bonds are called polar covalent bonds because there's polarization of the electrons in the structure. The polarization of those electrons can be visibly seen by inspecting a Lewis structure. Polarization will favor the most negative, the most electronegative element, which, by the way, has to be located on the far right, upper right of the periodic table. We will discuss that later as well. Group 14 through 17 form covalent bonds. If the bonds are different, if the atoms are different, two different atoms will make it by default a polar bond. We show you some examples here. They're all covalent. H with carbon is polar. Nitrogen with oxygen is polar. Chlorine with chlorine is nonpolar because they're not different. Boron with boron, nonpolar because they're not different. As it turns out, HF has a polar bond and is also a polar molecule. How do we know it's a polar molecule? That's where electronegativity comes in. Electronegativity is the ability of an atom to attract towards itself the electrons in a chemical bond. In other words, that element has the ability to invite the electrons closer to it than the other atom. We show you here what it looks like. You have a neutral atom, if you will, plus the negative electrons. They gravitate toward that neutral atom. Essentially, that neutral atom attracts these electrons to give it more of a negative charge, a partial negative. Okay? And keep in mind, it's all relative. Fluorine, by the way, is the highest, but it's all relative. So you have to look at which atoms are involved before you can make the decision. So, in the case of the covalently bonded hydrogen fluoride, and we still show you its Lewis structure, its Lewis dot structure, the lone pairs, attracts electrons, and therefore we use this arrow symbol with the cross on it to represent the direction of the electron flow toward the fluorine. So, that sign stands for a dipole moment, which means that there is a partial flow of electrons toward the electronegative group. So you essentially take the arrow and point it toward the most electronegative group. Okay? We like to differentiate this, however, from ionic bonds, which are complete transfer of the electrons from the electropositive part of the compound to the electronegative part. For example, potassium fluoride would leave potassium in an oxidized state, and fluorine would be in a reduced state, and it forms an ionic compound, an ionic salt. That is different from a partial positive or partial negative flow of electrons or movement of electrons. We show you these examples that we showed you earlier. We take a look at hydrogen and carbon. Carbon is more electronegative than hydrogen. Therefore, we draw our dipole moment arrow toward carbon. Oxygen is more electronegative than nitrogen. Therefore, the flow of electrons is toward oxygen. But in nonpolar molecules, there is no flow of electrons. We've used what we call diatomic molecules to show you this principle, meaning that only two atoms. It gets a bit more complicated with more than two atoms, but the principles are the same. The principle is this: electronegativity means that there is an atom with a higher concentration of negative charges associated with it than another atom. Electronegativity is the ability of that atom to attract the electrons toward it through that covalent chemical bond. We show you this periodic table to reinforce electronegativity. Electronegativity increases from bottom to top and left to right. I tend to draw my tables or use tables that show it in one direction instead of one goes up and one goes down. So increase is up and across. Okay, that's the direction of electronegativity. We show you some examples here just to reinforce it. Fluorine is greater than oxygen, greater than nitrogen, greater than boron, greater than beryllium, greater than lithium. And then we show you these other examples here. When we look at group 1, lithium is more electronegative than sodium, etc., etc. Okay? Then we show you in group 17, and then we show you what happens along the transitions. Now, take care, because there are some exceptions. This was simply to illustrate the overall trend towards electronegativity. There are exceptions to these. As a note, metallic character follows the opposite trend. So you want to know what's most metallic? You go the opposite of electronegativity. Okay? In terms of classifying bonds as being covalent or ionic, there are a couple of approaches to doing that. In earlier lectures, we taught you how to look at the periodic table and based upon the position on the periodic table, as in being in group 1 and group 2, with something in the far right side of the periodic table, for example, 16 or 17, we noted that that creates ionic compounds. We also said to you in earlier lectures that group 14 through 17 create covalent molecular compounds. We can also use math to make this determination. So there's a qualitative way of simply by inspection, knowing where it's located on the periodic table, and there is a math approach. The graph in this slide shows you the trend line for certain materials to help plot this out to give you an idea of what it's like to look at the percent ionic character versus electronegativity difference, and how that difference allows you to define whether it's covalent, ionic, or polar covalent. These values will sometimes differ slightly. In fact, in my own presentation, you will see a table that some view as being a little bit more precise. But in general, this trend works. If it's greater than equal to 2, it's ionic. If it's less than 2, it's polar covalent. If it's 0, it's simply covalent. Okay? So above 0 to less than 2 is considered to be polar covalent. Greater than 2 is ionic, and 0 is covalent. Some prefer to use a value of 1.8 instead of 2. And in some of my presentations, in this lecture, in this course, you will see the 2 value and you will see the 1.8. Okay? Typically, that difference doesn't matter when it comes to what we're hoping to accomplish in teaching you these trends and how to use the math to make that decision as well. So be aware of that there are some minor differences depending on whose table you use and when you use that table. Okay? So let's work through some examples here to see whether or not we can understand how to choose the type of bond. So we're going to classify the bonds as ionic, polar covalent, or simply covalent in these compounds shown here. Okay? We can follow the rule of 2 or 1.8 for electronegativity difference and look at the values on a table. So if we look at the values of H and Cl on a table, we'll find that the difference between the values are simply numbers posted in a table or on a periodic table. You will see that the difference between the electronegativity of H and Cl is 0.9, which is not large enough to make HCl an ionic compound. Therefore, the bonds between H and Cl, the bond between H and Cl, is a polar covalent bond. Consider potassium and fluoride. On the periodic table, the difference between potassium and fluoride is 3.2. That's much larger than the rule of 2, or 1.8. Therefore, the bond between potassium and fluoride is ionic. The 2 carbon atoms are identical, and therefore, by default, we know that it is not a ionic bond. It has no polarity. It is purely covalent. When the atoms are exactly alike, the answer is purely covalent. When the atoms are different, they may be polar, but to what degree are they polar? We use the values to calculate the degree of polarity. And those values are found on a table for electronegativities. There are some periodic tables that in fact have those values. We have such a table in these lectures. That leads us to further discussion about ionic bonds, which are different from covalent bonds. Ionic bond. The electrostatic force that holds ions together is an ionic bond in an ionic compound. So, we call it an ionic compound because it is held together by electrostatic force, meaning that there is a positive pole, a clear positive pole, and a clear negative pole. It is not a partial positive, it is not a partial negative. It is, in fact, a plus and a minus. We look at the electron configuration, and we see that we have one valence electron for lithium, and we have 7 valence electrons for fluorine. That means that we can put these together using the Lewis format for doing this. However, in the final structure, we completely transfer the electron from the lithium to the fluoride. So the key here is to view it as you would the classical Lewis structure for covalent compounds, and then simply transfer the connecting bond completely to the negative atom. Note that when we write compounds in chemistry, we write the electropositive part first and the electronegative part second. Okay? So when we do this, what we discover then is that the lithium part of this, the positive part, is isoelectronic with helium. We know it's isoelectronic with helium. It is not helium, but isoelectronic means that it has the same electron configuration as helium. Okay? So it has the same electron configuration as helium, as 1s2. We note that the negative part of the salt, the fluoride ion, or fluorine atom, has an isoelectronic configuration with neon, which fulfills its octet. Both of these fulfill the octet in being isoelectronic with atoms in the noble gas column group 18. So this is how we look at Lewis structures for ionic bonds. We can use the same format, but then we must remember to transfer the electrons from the electropositive part to the electronegative part, where we would normally have a full covalent bond. So, ionic bonds form with transfer of electrons from the cationic element to the anionic element, and we show you a balanced equation for doing that. When we take the lithium, it transfers an electron, it becomes oxidized. We take the fluoride and it accepts an electron and becomes reduced, forming a ionic compound which has ionic bonds. So let's play with this. Let's use an example of an ionic Lewis structure. Let's do it for aluminum 3 oxide. So we have aluminum 3 oxide. We note that the aluminum has 3 valence electrons associated with it. Oxygen has 2 available sites from its 6 total Lewis dots associated with it. So, the art to this is to mix these so that we get 2 atoms of aluminum and 3 atoms of oxygen. If we take a look at its electronic state, aluminum is oxidized to a +3 and oxygen is reduced to a -2, and we have to take this into account as we walk through the structures. So what we discover then is that the best ratio for electronic neutrality of this compound is to have 2 atoms of aluminum and have 3 atoms of oxygen. So we write out the electron configuration for each of these so we can follow the flow of electrons or where the electrons will bond and form some type of hybrid interaction, which you will learn about hybridization in the next chapter. So we take the aluminum, 2 atoms, 3 atoms of oxygen, and we transfer the electrons from aluminum to the oxygen side. We check our electron balance because we have 2 aluminums times plus 3, that gives us a plus 6. We check the electron balance on the negative side, the reduced form, the reduced atom, 3 times minus 2 gives us minus 6, so it's electronically neutral. And what we find is that these species are both isoelectronic with neon. That satisfies the octet rule for this ionic compound. Another way to visualize this is shown on this slide, where we have the donation of 3 times 2 electrons, and we need 2 times 3 electrons. And so we have that balance of donating and accepting electrons is perhaps a better way to look at it. And we do that, and we show you the diagram where aluminum transfers its electrons to oxygen, and it forms this ionic compound. We then show you that at structure 1, which is the true ionic structure for this. However, just for visualization, we show you the B structure in this slide, which shows where the dots will connect in a classical Lewis structure, and we draw a classical Lewis structure for it as C. But keep in mind, ionic compounds look like A, more like A than they do like C. But for instructional purposes, I wanted to be able to show you this, and it's from this point that these atoms transfer the electrons to the most electronegative part of the molecule. In terms of bond strength for ionic compounds, when we think of their bond strength, we think of what's called the electrostatic lattice energy. So what is lattice energy? Lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. In other words, you're basically degrading the compound into its gaseous ions as a way of determining what the strength of that ionic compound or the ionic bonds within that compound or the electrostatic forces within that compound are. That's called the lattice energy. So essentially, the lattice energy is a measure of the strength of bonds in the ionic compound. And that potential energy is proportional to a constant, and it is strongly influenced by the size of the charge of the ion. Okay, so we show you the equation. So the size of the charge becomes a key consideration when considering the strength of the bonds within an ionic compound, and that is a take-home point. Okay? The strength of the ionic compounds, the bonding in that ionic compound, is greatly influenced by the magnitude of the charge, whether plus or minus. So, what do we know then? We conclude then that lattice energy increases as Q increases and or radius decreases simply by paying attention to the math. We decrease the radius, the lattice energy increases. We increase the charge, the lattice energy increases. And we show you some examples here where we have magnesium fluoride, and we note that magnesium has a +2, fluoride -1. Size of that charge is +2. Note that in magnesium oxide, we have 2 minus charges, and note that the lattice energy is higher. However, when we have compounds that have charge of +1 and -1, which is lithium fluoride or lithium chloride, that value is lower. and it's lower for the chloride than it is for the fluoride. And this is all related to the charge and the radius. So the key point here is that lattice energy increases as Q increases or as radius decreases. And we must remember to pay particular attention to the magnitude of the charge. We show you a table here of several values for inspection so that you're aware of what the values look like. If you take a look at this, you'll be able to spot those trends about size and about charge. Now, getting this information is not so straightforward, but it can be acquired through a process called the Born-Haber cycle. The Born-Haber cycle is a method of analyzing reaction energy. That's what it does. It analyzes energy of a reaction. It is primarily used to calculate lattice energy since it cannot be measured directly. In other words, we cannot directly measure the lattice energy of an ionic compound. So we indirectly get it by putting the pieces together. And that process is called the Born-Haber cycle. So we take a look at the enthalpy values, or delta H, of processes related to the final ionic compound, and we add them together, we sum them to get an overall delta H for the process. That's how we get our lattice energies, and we show you the example here for lithium fluoride. We start at the bottom left of this diagram. Essentially, we want to go to the right, but that process is not available to us, so we kind of go through the process of dissociation and subliming it, takes it up to the gaseous state. Then we take the gaseous state into the ionic state, and we see the ionization energies there and the negative electron affinity values. We see these values, delta H, through each of these steps. Step 1, 2, 3, 4. We finally get to a gaseous ion. That gaseous ion falls to a lower energy state, the solid lithium fluoride, through our delta H5 with its associated value, a negative value there. We put these values together, we sum these values, and we get the overall negative 594.1 kilojoules for this. And this is the value of the Born-Haber cycle. It allows us to determine those lattice energies. Lattice energies help us to understand what the strength of an ionic bond is. We can acquire data about the strength of that ionic bond. And the ionic bond strength, lattice energy, is proportional to its charge and inverse proportional to its radius. So that's it for Lecture 1 of Chapter 7, Chemical Bonding and Molecular Geometry. Lecture 1 of 2, Chapter 7.